All right, guys and gals, let's talk about probability. So first off, the fundamental counting principle. If we've got m different decisions, we can make them lowercase m ways, and another decision n that can be made n different ways. The way we can make those two decisions together is m times n. So for instance, you got 5 pants and 10 shirts. Well, if you're just making outfits from those, for the first pair of pants, you got 10 options. For the second pair of pants, you got 10 options, and etc. So if you do 5 times 10, that's 50 different options. That's all the fundamental counting principle says. Similar thing here, if we have even more events, you can have M, N, P, how many ever decisions you need, how many ever events you need. 3 cone sizes, 15 flavors, and 8 toppings. Well, that's 3 times 15 times 8. Just type that in the calculator. You get 360. So there's 360 different ice creams you can make with 3 cones, 15 flavors, and 8 toppings. Now let's assume you only choose 1 flavor and 1 topping. If you do more, it gets a lot more complicated. Let's talk about a license plate. So it says 3 letters followed by 4 digits. So 3 letters and then 4 digits. Letters. How many letters are there? Well, there's 26 letters in the English alphabet. So that means this first item has 26 possibilities, another 26 possibilities for the next item, and another 26 for the third item. So that's could be like A, B, C, A, Z, D, whatever. There's 26 options on each slot. Now the next has 4 digits. Well, how many different digits are there? Well, there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 digits. So each of those has 10 possibilities. So basically we have 1, 2, 3, 4, 5, 6, 7 different events that are just, happening. So we have to make that many different decisions. We multiply all that together. 26 times 26 times 26 times 10 times 10 times 10 times 10. That's going to give us this number right here. Now you might be thinking, well, isn't there an easier way I can type that in? And absolutely is. If we use exponents, we can say this is the same as 26 to the third, the number of different choices we have, how many times we're doing the choices, times 10 to the fourth. Again, the number of choices we have, how many times we're making that choice. Type that in the calculator, we should get the same thing. And there we go, same thing. That makes this one a little easier to write. We have 12 true or false questions. So there's either true or false. You got 2 options, but you got that 12 times. So 2 to the 12th power, or 2 times 2 times 2, etc. But exponents are very handy. Let's use them. 4,096. So we've got a multiple choice test, 12 questions. There's 4,096 different possible sets of answers you could come up with. You could have all true, you could have all true, and then 1 false at the end, 1 false in the middle, all kind of different options. 4,096 in fact. This one has a 4-digit code. So 1, 2, 3, 4. It's a digit, so that means 10, and 10 options, and we're doing that 4 times, which that one you can probably do in your head. It's 10,000. All right, so that's the fundamental counting principle. Nothing too much to that. Now we need to talk about the factorial symbol. So if we have n factorial, that's the exclamation point, that's the product of all the numbers, the natural numbers from n to 1. So you go down, just 9 factorial would be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And so that equals 4. You can do it here. 9 times 8 times 6 times 5 times 4 times 3 times 1. It gives you 362,880. Now this particular calculator that we use has the factorial symbol. Shift and the inverse button. Same result. Now it's important to note that 0 factorial is actually 1. Okay, so that's defined as 1.
Victoria Carrier, report to the office, please. Victoria Carrier. Landon Vitrine, Chloe Bertrand, report to the office.
So that one is very important. It's defined as 1. So we don't have to worry about dividing by 0 factorial because it's just 1, it's fine. For these, we're just going to type in the calculator. 12 factorial. Okay, I'm just going to screenshot that. And then 8 factorial. So it's real easy, just type in the calculator, nothing to it. If you don't have the factorial button on your calculator, just do it the long way. Now if we're dividing, let's think about what this means. I'm gonna do it over here. 17 factorial divided by 11 factorial. So I know that's 17 times 16 times 15, and yes, you could just do this in the calculator, times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 11 factorial. What is 11 factorial? Well, it's 11 times 10 times 9 times 8 times 7, 6, 5, 4, 3, 1. So those two pieces will cancel out. So this is actually equal to this product right here. That's 12. So if we do 17 times 16 times 15 times 14, it's 13 times 12. We get the same thing as if we do 17 factorial over 11 factorial. And here it is right here, so you can compare. Same thing. All right, so for the calculator, it doesn't make much of a difference, but if you had to do this by hand, it would definitely save yourself a lot of time if you just thought about it canceling. Also on the ACT, I think I've seen it this way a few times. They might have like 17 factorial divided by 15 factorial, so you just have to do 17 times 16. Again, use a calculator if you got it. Now we need to talk about permutations. Okay, the notation we're going to use is NPR. Okay, we use a permutation when order is important. If the order we line items up in matters, then we're going to use a permutation. So let's say we're trying to find a first, second, third place winner in the race. Well, first and third place are definitely not the same thing, so the order would matter. Later, whenever we have things that the order doesn't matter, it's just selecting 3 objects, that's going to be called a combination. Here's the formula. N factorial over n minus r factorial. It's not that bad of a formula, but also the calculator does have a button for it. I'll show you in a second. N is your total, how many things you're looking at. If you got 27 people, then it would be 27. If you have 27 people and you're trying to find first, second, third place, then R would be 3. So let's just do that. Let's say we have 27 racers and we're trying to find first, second, third place. That's going to be 27 factorial over 27 minus 3 factorial. That's 27 factorial over 24 factorial. So you can type that in the calculator, or you can do 27 times 26 times 25. Either way we do it. We'll come up with 17,550. That's how many different ways we can choose a first, second, third place person out of 27 people. Now here's a little shortcut. What happens if we plug in n right here? Well, that would be n factorial over 0 factorial. We know that's 1, so that's equal to n factorial. So npn is just n factorial, same thing. Okay, let's look at how we could use that. How many ways can we arrange the letters in the word dinosaur? Well, there's 1, 2, 3, 4, 5, 6, 7, 8 letters. And we're arranging 8 of those letters. They're all different, right? Yeah. So there's no repeats or anything to worry about. So 8p8, that's the same as 8 factorial. Also, while we're here, let's go back for a second, sorry. 27p3 should be this number, right? So let's see how to do that on the calculator. 27, and if we look, the multiplication, shift, multiply 3. We get the same result, 17,550. Okay. 8 factorial, we did that a second ago. 40,320. That's how many ways you can arrange letters in dinosaur. Over 40,000 different ways. Okay, 7 students competing, first, second, third place. That's 7p3 this time. We're not choosing all the different places, we're just choosing the top 3. So 7p3, 210. Okay, a few more examples. This girl's taken 4 classes, history, algebra 2, English, and chemistry. So this is a 4p4. So the order matters, right? It's different taking history than algebra than it's taking algebra than history, right? The order you do them in matters. So it's not the same class. 4p4, that's just what? 24. It's 4 factorial, which is 4 times 3 times 2 times 1. So yeah. 16 players, that's what we're starting with. That's our total. We're choosing 9 players. Now you might be saying, well, that's just taking 9 players. How does that order matter? Well, if you got your best player and your worst player in there, you know, they're different people. So the order actually does matter. You can't have the same person batting 9 times, can you? I don't think so. Not a baseball slash, yeah, softball person, but I don't think you can just have the same person batting every single time. Well, it gives us what, 4 billion? Yeah, 4 billion some different possibilities. Okay, we got 28 students. We're selecting a representative and an alternative. So that's 2 people we're choosing, and they're different. They have different value. So the order does matter. 756. So councilman, representative, president, vice president, something like that. The positions are different, so their value is not the same. So that means the order does matter. Sorry about that. Now let's say we got a repetition in our word. So we're going to arrange this word, but if we notice, we got 2 O's. So we have 10 factorial because there's 10 letters. You can count, or it tells you right there there's 10 letters. But we have a double O, so that's 2 factorial we got to divide by. We divide by the repetitions. And that's going to give us whatever it gives us. That many. If you look at the next word, disappear, we've got 2 different repetitions. We've got 2 P's, we've got 2 A's. And it's 9 letters. So we got 9 factorial over A, we've got 2 of them, so 2 factorial. P, we got 2 of them, so 2 factorial. Let's say we had like 3 P's or something. If we had 3 of them, we do 3 factorial, how many ever repetitions we have. Because just taking out the different possibilities of that order. Okay. 9 factorial over 2 factorial times 2 factorial gives us 90,720. Okay, moving on along. Let's talk about combinations. Now, this is where it gets to order not mattering. So, similar notation in CR for combination this time. And there's a formula. Again, the calculator has a button, we're just gonna use it. But if you have a different calculator, or if for some reason you need to do it by hand, that is the formula. Now let's see what would happen if we plugged in here. Plugged in, that would be n factorial, that would be 0 factorial. So that's gonna be n factorial over n factorial times 1, which is just, well, 1. So we got 16 close friends, and she's gonna just pick 5 at random for bridesmaids. So 16 C5. It's not the top bridesmaid and the bottom bridesmaid, it's just, I'm picking 5 bridesmaids. So the order does not matter. $4,368. We got, 24 students. How many ways can we grab 8 of them? 24 C8. It's just 8 random kids. It's not any particular ones. The order doesn't matter. We're just choosing 8. You could choose Sally first, or you could choose Sally last. It'd be the same setup. $73,500, $735,471. So like in this example, it doesn't matter if you pick Bob, Jim, Sally, how many ever. It doesn't matter if Sally's first or if she gets picked last. It's the same group of people. We think back to that baseball problem. Where is it? Let's say Sally's your best and Jim's your worst. Well, then it would make a difference if Sally was first, if your best was first, or if your best was last. That would be a different order. Whereas here, it doesn't matter which order you put them in. They're the same. Abby is adopting kittens from the pet store. There's 18. She's going to just randomly grab 2 of them. How heartless. Grab all 18, right? 153 possibilities. 12 employees. They're going to choose at random just 4 people for the Sunday evening shift, not a manager, co-manager, anything like that. It's just 4 people, 4 workers. All of equal weight, all of equal value. Order you choose them in does not make a difference. $4.95. Okay, 85 players. So they're going to choose 3 to represent the team. Any 3 players, doesn't matter if it's the ball boy or the quarterback. Or it doesn't matter, it's just 98,000 different possibilities. Let's look and see the difference between permutations and combinations, when to use which. Remember, permutation, the order matters. Combination, order does not matter. So here's 12 examples we're going to look at. Store has 30 different candy bars, and you're going to grab 4 of them at random. Okay. There's no one candy bar better than another. It's just grabbing 4 candy bars. It doesn't matter if you choose the Hershey's and then the Mr. Good bar, or the Mr. Good bar and then the Hershey's. You have the same group at the end. That's a combination. And you do 30 combination 4, and you know, you can just type that in the calculator. We'll do that. You can do that on your own. You got that. Okay, we're having a lineup. Anytime we have a lineup of something, we're talking about the individual items being different. So we have 13 different students lining up. That's a permutation. Now you could do 13p13. You're lining all 13 of them up. Or, you know, that simplifies to 13 factorial. You get the same thing either way. So 13p13 or 13 factorial. Next, how many ways can you make a 3-letter word, well, arrangement, out of the letters in the word trapezoid? So 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. So we're lining up the letters. That's the order matters. We're making different words. So that's 9 total. You're going to take 3 of them. On the next one, we're choosing 2 books from a shelf of 40 books. So it doesn't matter if you get Treasure Island, then Crime and Punishment, or Crime and Punishment, then Treasure Island. It's the same 2 books. So that's a combination. All right, we got first place, second place, and third place. That's definitely different values, so that's a permutation. 12p3. Mrs. Sullivan is going to choose 2 students to help put the calculators away. So it doesn't matter if you choose Bob and Sally or Sally then Bob. It's the same 2 students. That's a combination. 27C2. We have enough different tickets to play 6 different games at the amusement park. There's 14 games, and you want to choose 6. Okay. So it doesn't matter if we do the ring toss and then the whack-a-mole, or the whack-a-mole and the ring toss. No, it's the same group of 6. That's a combination. The order does not matter there. But on this one, we're lining up people. We have a lineup. It doesn't matter if it's a baseball lineup, football lineup, whatever kind of lineup. Those people, those items are individuals. They're distinct. If they weren't, then it doesn't matter how many you had. There'd just be one arrangement. So if you said that all the players were the same, then it doesn't matter if you put player number 1 first or player number 7 first. That would be a combination, but this, in fact, is a permutation. The order does matter. So again, you could do 9p9 or this 9 factorial. Seven students work together on a project. How many ways can their teacher choose 4 to present the project? So we're choosing a group of 4 people. It doesn't matter if you choose Bob, then Jim, then Sally, or Sally, then Jim, then Bob. It's the same group. So 7C4. 18 offensive players on a hockey team. How many ways can you choose a left wing, center, and a right wing? Those are different positions. The order would matter that you pick them. You wouldn't pick your left person to be your center person, I don't think. I have no idea about hockey, but they're definitely different positions. So the order you pick them in matters. 12-letter arrangements can be made out of using letters in the word Indianapolis. Again, we're lining it up, so it's going to be a P. Now this one, we're doing 12P, 12, but we're going to have to take out the repeats. So we're doing 12 factorial. We're going to take out the repeats. I got an I, 3 I's, so 3 factorial. N, that's it, 2 factorial. D, no, A and A, that's 2 factorial. That's it. So whatever that gives you, would be how many ways you can arrange that word Indianapolis. We got to divide by the repeats because it doesn't matter if we use this A first or that A first. We can't distinguish them. So that's why I had to take out that 2 factorial right there. So there are 26 goldfish in a tank at the store. How many ways can Ben choose 5? That's a combination, 26, C5. All right, and that'll wrap up the first section of probability. See ya.